So I don't know how many people attend this meeting year over year, but as Jan said, 2 years ago, Doug Kothe came, he's the project director, and gave an overview of the ECP, and last year Andrew Siegel came and gave a discussion of the applications that we're investing in. This year, what I'd like to do is focus on the software technologies. So I'm going to start with an overview of the ECP for those who are not familiar with it, briefly touch on the other areas, but dive a little bit more deeply into the software technologies. Because I'm representing such a large project in 45 minutes or less, it will, by nature, be very high level. And so if you want additional information or more technical details, I'll be giving you pointers to places where you can access that information. So what is the Exascale Computing Project? So we are a large research development and deployment project that is focused on accelerating a capable exascale computing ecosystem. So what does that mean? As I just mentioned, it's really focused on what are the applications that will be ready to go day one when the exascale computers are delivered? What kind of science will they be able to deliver? What are the software technologies that are needed to make those machines a success? And that our efforts are to complement the efforts of the vendors, the high-performance computing vendors, and then how do we integrate with those computer facilities? So we are part of a larger initiative in the Department of Energy called the Exascale Computing Initiative. And so there are really three components to that. The first is the ECP, which I'll be talking about today. The second is the procurement of the systems. So that's one thing to be very clear on, is the Exascale Computing Project is not buying any computers. We are developing applications, software technologies, and integrating in with the facilities and investing in advanced research for computer architectures, but we're not in charge of procuring those systems themselves. And so that gives us an additional opportunity for project management and collaboration with the facilities at the Department of Energy labs. And there are three of those that I'll be talking about a little bit later, one at Argonne National Lab, one at Oak Ridge National Lab, and one at Lawrence Livermore National Lab. And then finally, in some of the other application offices at the Department of Energy, they have invested in applications and mission areas that are very specific to their needs. So this is in biological and environmental research. So for example, I think climate modeling, genome analysis, basic energy sciences, materials, chemistry, et cetera. And then the NNSA, which is the National Nuclear Security Administration, which is focused on things like stockpile stewardship for our nuclear weapons. And so large, multi-scale, multi-physics type applications that are being invested in. So what do we mean by exascale? So exascale nominally is 10 to the 18th flops per second, but in our minds, that definition is not enough. So if you take a look at the blue box, this is on the IBM Sequoia machine at Lawrence Livermore, and you can see that the theoretical peak is about 20 petaflops. LinPack, we did great, we got about 17 petaflops. But then if you start looking at different applications, as you all know, you get very different levels of performance out of those machines, right? Some can get as high as 11 or 12 petaflops out of 20. Some may only achieve 0.6. And so when we talk about what we want out of exascale machines, these will be designed to be 50 times the performance of the Sequoia class machines, the 20 petaflop machines by flops. But what we're talking about for ECP is we also want 50 times the scientific capability. And so when we define our application challenge problems, or the applications that we're delivering, we are requiring each application to define what is the science grand challenge problem that they can't solve today that requires exascale computing, and then what is their measure of work, right? What is the rate at which they can do work? And for us to be successful as a project, we are required that many of our applications achieve 50 times that rate of work, okay? And that can be challenging more than just achieving the peak performance. So that's how we're defining success for our applications and what we mean by exascale, a 50x improvement in the scientific capabilities that we can deliver for the nation. So I'm probably preaching to the choir on this, but thought I should include it. Why is high performance computing hard, and why is it getting harder? So increasingly, as you know, we're getting more and more and different kinds of nodes, processing units, graphical units, accelerators of different kinds. And so applications are required to find increasing amounts of concurrency just to keep up. In addition, over the last many years, flops, when I was in graduate school, flops were free and communication was very expensive. Communication was free. The flops were expensive. Now it's reversed. And so moving data is very costly relative to computation. And so increasingly we're needing to find ways to hide that to improve latency. In many cases it makes a lot more sense to recompute information rather than doing data movement and looking it up. Things like I/O, viz, and analysis have become major bottlenecks. And so there's a lot of work going into what do we need to do to make that less of a bottleneck for the application so they can get their science done. Future architectures are much more uncertain than the architectures that we have today, and that's leading to just an explosion of interesting opportunities for computer scientists who are exploring lots of new programming models, different approaches that supplement the traditional MPI plus X, where X is OpenMP or CUDA or what have you. So there are a lot of different programming models now that the applications need to try and understand and explore and understand what's best for them. And that's both on node and then internode. Things like task-based parallelism. Does that have a role for applications in the future as opposed to the traditional bulk synchronous MPI type distributed computing? Global arrays, UPC++. Again, lots of things for the applications to try and take into account when they're thinking about what is it that I need to do going forward. And so that's causing a lot of thinking and rethinking about algorithmic implementations and just the algorithms themselves. So increasingly, we're reducing communication and data movement. We're familiar with lots of examples, for example, in algebraic multigrid, where instead of doing multiplicative type operations that require a lot of communication, if you switch over to additive, the convergence of the method is slower, but overall, because it doesn't require as much communication, you get to the answer much faster. So things like that, where you're replacing communication for, computation for communication, and overall getting a win. So increasing locality awareness, this is something that the programming models need to expose, and this is some of the gaps that we have in our current programming models. Mixed precision. Is this something that can be valuable? It's already proven to be incredibly valuable for machine learning type techniques, as we've seen with the Gordon Bell winners from supercomputing this past year. But I think it's a little bit harder to pin down in traditional PDE, partial differential equation type applications. What does that really mean for PDEs? And then fault resilience. A lot, for many, many years, fault resilience, it's going to be a problem, and then it's not a problem. So are we finally at the point where it's a problem? So a lot of people are saying, no, we're still going to get through this round of computers as well. So that'll likely be handled outside the applications. And then looking at brand new algorithms, or in many cases, algorithms that had been looked at maybe 20, 30 years ago but dismissed, are now coming back into vogue because it's much more cost effective on the architectures of today. So for this, I think about things like higher order methods. So for discretization techniques, things above second order, fourth, sixth, eighth order methods. These had been largely dismissed because they were too expensive and you weren't really getting bang for your buck because you were having to move a lot of data and you weren't getting additional accuracy out of it. Sorry, you were having to do a lot of, I keep reversing those this morning. See, it's early. So, but now, because you're bringing all of that data in and you're doing high order computations on it, a lot of arithmetic for the amount of data that you've moved, you're able to get much more bang for the buck. We've been experimenting with these a lot at Lawrence Livermore, and we're finding really good return for investment, both in terms of weak scaling, strong scaling, on-node performance. They've been really good. I've already mentioned on-the-fly recomputation versus table lookups, and then another interesting algorithm that's come up in one of our applications is particle algorithms. For example, in small modular reactors doing neutron transport, particles are moving around, and traditionally those algorithms were organized and parallelized by the particle itself. So you'd follow a number of particles in your parallel partition, and whatever is happening to those particles, it just follows along. So that ends up in a lot of different branches in the code. They find that that doesn't perform very well, for example, on GPU accelerators. And so what they've done is they've reorganized and looked at an algorithm that was considered, again, 20, 30 years ago. And they're looking at organizing it now, rather than by numbers of particles, by the events that are happening. And so when you take all the particles that are having a similar sort of event and put them on a single GPU, they're getting much better performance. In fact, they're seeing a factor of 40 times more performance when you look at parallelism in that way rather than the traditional way it's been done. So these architectures are causing, again, lots and lots of rethinking of the algorithms, how they're implemented, and what algorithms we're even using. So now for the technical areas in the ECP, we have all the components we believe to create the capable computing, exascale computing ecosystem. I've already hinted at this. The three that I'm going to talk about today are application development. I'll give a high-level overview of that and point you to more information. Hardware and integration. This is really the place where we're interacting with the high-performance computing vendors in the US and also with the facilities at the Department of Energy labs. And again, a high-level view of that. And where I'm going to spend most of my time is really on software technology this year, and do a bit of a deep dive on the kinds of things that we're doing in software technology, the areas that we're looking at, and how we're planning to deliver those technologies to the applications and to the facilities. So starting with application development, the goal here is to develop and enhance the predictive capability of applications that are crucial to the Department of Energy. So we've got 25 different applications that are basically highlighted in the bar across the bottom in those areas, and then 6 co-design centers that are focused on computational motifs that are important to multiple applications. So the ideas here are really about thinking about what's the next generation of physics, the systematic improvement that we need for exascale readiness and utilization of those systems, and then the demonstration of that capable system that we talked about earlier, that 50x in science work rate. So the 25 applications are in these mission areas. So national security, these are at the 3 NNSA labs and are largely targeting the multi-physics applications associated with stockpile stewardship. So these are very high energy density physics type applications, multi-physics applications, a lot of complex physical processes that are being knit together. And then at Sandia National Lab, they're focused on some of the applications around, for example, hypersonics, so re-entry vehicle simulation environments, and what are the impacts of that. So lots of multi-physics, lots of coupled calculations. And then the other areas that you can see across the top here. So we've got energy security, which is looking at a variety of different kinds of energy and how that can play a role in the systems that we have. So looking at wind plants. So how do you model a wind farm when you have 100 turbines on some, topologically interesting domain? And what are the impacts of how those turbines are placed in terms of downwind utilization? That's a very large scale, again, multi-physics type application that requires not only modeling the turbines themselves and how they're bending and flexing in the wind, but then also the interaction of those turbines with each other. Design and commercialization of small modular reactors, I already mentioned that one a little bit, neutron transport. Fission reactor design, subsurface, and I'm going to talk about that one in a little bit more detail because I thought it might be of interest to this audience. Scale up of clean fossil fuel combustion, catalyst design. So lots and lots of different areas in the energy sector that we think are important for the DOE mission. For economic security, an interesting application is additive manufacturing. As many of you know, there's an increasing push towards understanding the processes associated with additive manufacturing and whether or not you can make qualifiable parts on a one-off type basis with these techniques. Because of the way they're often done, like with laser sintering type processes, they create different kinds of stresses, different material properties within the final parts. And so how do you know that that part is going to perform as you expect? So using multi-physics, multi-scale modeling to understand those processes and then hopefully create those qualifiable parts is something that we're interested in looking at. New areas for us are things like urban planning. And so here you can think about what's the interaction between a micro weather type simulation and building efficiencies, and how do those two things play off of each other? Power grid, looking at planning for the power grid, security, and then seismic risk assessment. So coupling earthquakes to how buildings respond in an earthquake type scenario and doing that risk assessment. Many of you probably know the Department of Energy is one of the biggest funders of basic sciences, particularly physics in the United States. And so we have a lot of scientific discovery type missions that we're following. So things like astrophysics and understanding what's going on in the heavens above us, right? A lot of large-scale facilities where they're generating enormous amounts of data from light sources, various different kinds of light sources. How can we take that data, understand it, and provide insight in very fast turnaround times for the physicists who are using those facilities? Chemical elements and demystifying their origins. ITER, looking at fusion, and operational performance. And then, of course, the Earth system. Here we're talking a lot about Earth system models, so climate modeling in particular, looking at crop analysis, catalytic conversion, biomass, derived alcohols, and then metagenomics for biogeochemical cycles. And then finally, excuse me, in the last several years, the Department of Energy has partnered with the National Institute of Health on something called the Cancer Moonshot type application, where we've been investigating how can we use high performance computing to help develop and understand different kinds of mechanisms associated with cancer. And that's something that we're supporting as part of the Exascale computing project as well. Oops. So some of the common activities and challenges that have come up for the applications teams in their development of these areas is, porting to these accelerator-based architectures. GPUs in particular is the current generation that they're focusing on. Exposing additional parallelism in the algorithms so that they can keep up with the amount of parallelism that's available on the machines of today. New multi-physics capabilities and coupling the codes together, and what does that mean? What does that look like? New mathematical approaches, new models that can bring increased fidelity, increased accuracy into the physics that they're modeling. Looking at algorithmic or model improvements, and then finally leveraging optimized libraries, so better linear solvers or nonlinear solvers, and how can they take advantage of those and knit those into their application domains. So one example that I'll dive in a little bit is the subsurface carbon capture, fossil fuel extraction, and waste disposal. And this application is really focused on looking at the multi-scale modeling that's needed to understand the safe and efficient use of subsurface areas, well bores, et cetera, for CO2 sequestration, for the extraction of fuels and petroleum, and then understanding and being able to predict that. So this is a multi-scale application where you've got distances on the order of kilometers for the reservoir or the field, and you've got also distances on the order of microns when you're looking at cracks that may be occurring in well bores, and understanding what are the implications of those two physical processes interacting with each other. And so what this application is doing is it's taking a large-scale reservoir simulation model called Chombo Crunch, which is based on the Chombo adaptive mesh refinement libraries developed at Lawrence Berkeley National Lab. That does Navier-Stokes type flow, Darcy type flow. It's got multi-component reactions that are incorporated into that application. And then trying to couple that with GEOS, which is a geomechanics and fracture modeling tool developed at Lawrence Livermore National Lab. And they're using operator splitting techniques to do this coupling of the two different types of applications. And so they're developing a brand new multi-physics capability. That's one of the challenges that they're striving to overcome. They're needing to port this to an accelerator-based architecture. So in order to look at performance portability, which I'll talk about later, they're looking at domain-specific languages and seeing whether or not that can be used to abstract away the details of the architecture underneath, and developing parallel communicators that improve performance, et cetera. And then leveraging optimized library. In this particular case, linear, nonlinear libraries from the PETSI and Hyper tools developed at Argonne and Livermore National Lab, the adaptive mesh refinement in Chombo, and HDF5, which is an I/O library. So I included this list of applications. I'm not going to speak to them here, but I wanted to include them in the slide deck so that you could take a look later and I'd see if there are any that particularly interested you that you wanted to follow up on later. So finally, in the application space, we're looking at co-design, and then these are really the centers that we've created that are focused on motifs that are common across many different applications. So for example, structured grid calculations or block structured adaptive mesh refinement is being done with Amorex. SEED is looking at next generation discretization, high order methods like I mentioned earlier, and whether and how those can be used in lots of different applications. And then yesterday we heard a lot about machine learning, and we do have a co-design center that's focused on that called Exalearn, which is looking at different kinds of methods that will tackle really what's needed in the facilities by and large for the Department of Energy. So if you want more information about the applications, it's available on our website, which I'll have a link to later. And there's also an applications assessment report that will be coming out later this month that has a very comprehensive description and assessment of the 22 applications. And by comprehensive, I mean order 5 pages apiece. So, and it's basically something that'll be available in March. So now I'm going to switch gears, talk a little bit about hardware and integration, which is the second component for the ECP that I'll be talking about. And this is really focused on our interactions with the high-performance computing vendors and our interactions with the Department of Energy facilities. So in terms of the Exascale computers that are going to be deployed at the Department of Energy, this is the roadmap that shows our current generation of computers. The ones that are just about to be retired are over here on this side, left, right. So for example, the Titan system and Sequoia system are going to be retired later this year. And then as you move this way, you've got systems that are either just coming online. So for example, the Summit system and Sierra system at, sorry, there it is, at Livermore and at Oak Ridge. Perlmutter has just been announced. That's the next NERSC system at Berkeley National Lab. The RFP for Crossroads, which will be the next big system at Los Alamos, just came out a month or so ago. And then finally, we'll get to our Exascale systems. So that's the Frontier, the Aurora, and the El Capitan systems at Oak Ridge, Argonne, and Lawrence Livermore National Lab. And those are scheduled to come out in the 21 through 23 time frame. And so that's the time frame that we're targeting with the Exascale computing applications that we're delivering. So in terms of what hardware and integration is really focused on, they're focused on being the glue, really, that links the applications and software technologies that we're developing with the facilities and the high-performance computing vendors. So they've got a number of activities with application performance engineers that are focused on trying to make sure our applications really sing on those machines. What's the deployment model for the software technologies that I'll be talking about in a moment? How can they help us manage the resources that the facilities are making available to us? And then finally, the path forward program element, which is a large research activity that's funding efforts at the computer vendors, 6 computer vendors in the United States, that's looking at what's the R&D that's necessary for viable exascale computing systems. So this program element's been running for several years and actually concludes in 2020 because all of these technologies needed to be available for deployment in the exascale systems, which I said are coming online in the 21 through 23 system. So it was a large project, total investment of over $400 million, including the contributions from the companies, where they looked at novel memory architectures and high-speed interconnects and system reliability. Lots of different components that are necessary to make exascale computers successful. And what we have found is in the RFPs for the exascale systems, for the Coral 2 procurement systems, is that there has been a return on investment where we have found that the bids that were received, which are still under negotiation, created Exascale systems that were affordable to us that we wouldn't otherwise have been able to achieve without this program. And so for that, we say thank you to Path Forward. And so finally, I want to talk about software technologies in a little bit more detail. And this is really focused on well, I'll start here. It's focused on the ecosystem for software technologies that are looking at what's needed by the applications in several different areas, ranging from programming models and runtimes to development tools, mathematical libraries, and then I/O, data visualization, et cetera. How is that ecosystem going to work? How will things be deployed and delivered? And working then with our collaborators, which of course are the ECP applications, the facilities, the vendors, and the broader community. So the bottom line is that, and that I'm going to talk about today, is that we're developing over 89, 90 open source products that will be used by the applications, deployed at the facilities that are available for use by folks in this room, if you'd like. We're looking at deploying these through software development toolkits, which are fairly widely used out in the community, but are newer for high-performance computing and numerical methods. And so we'll talk about what that looks like within the context of ECP. And then also deploying it through the Extreme-Scale Scientific Software Stack, which is E4S. And again, the idea here is this is a comprehensive software environment that makes it easier for applications to take advantage of the technologies that are developed as part of the software technologies effort. So we're working on the products that we think the applications need now, and also that we think the applications will need in the future for the Exascale machines, even if they haven't quite realized it yet themselves. So the key themes of what we're looking at in the software technology space is making sure that the algorithms and software work well on emerging high-performance computing architectures. So I talked about that at the beginning of the discussion today. High-order methods, replacing computation with replacing communication with computation. Once again, I mixed them up. Looking at high concurrency node architectures, advanced memory systems, what's needed to support those and support them efficiently and as easily as possible for the application teams. And then trying to make sure that we're sustainable. And there are a number of different ways that we're doing that, but one of which is through the use of APIs, standard APIs, where we're involved in many different efforts that are trying to advance those in ways that support what we need for exascale computing. In terms of the software categories that we're working on in ST, I think there are three basic types. One is it's basically very well-known software libraries that are being developed, and we're developing the next generation of those that are going to be needed on the exascale computing architecture. So these are widely used products like MPI-CH, OpenMPI, PETSI, Trilinos, et cetera. The things you may have heard of and maybe already use. Some lesser known products, but they address key new requirements. So here I'm particularly thinking about things like performance portability. So we mentioned earlier that the architectures are changing a lot, and so increasingly software libraries, applications are looking to abstract away the details of those underlying architectures in ways that make sense. So the Department of Energy has been investing in several different technologies, and in fact I think later today there'll be a talk on Raja, which is one of those infrastructures to help with that and what those abstractions are. Another thing that's increasingly important, for example, in multi-physics applications is that when you try and knit lots of different packages together, just building them together can be a challenge. And so things like the SPAC package manager, which I'll again mention a little bit later, help ease that burden. And then finally, lots of new products that are under exploration for emerging requirements. So here I'm thinking about how the architectures are changing and the fact that you need more tools to address those memory hierarchies and things like compression. How can you reliably compress data to effectively increase the size of your memory footprint without sacrificing accuracy or fidelity to your physics? So I'm listing just some example products that we're working on in ST. So MPI, of course, is the backbone of most applications and widely used. And so There we're looking and exploring, open source implementations of MPI. What are the features that are going to be needed for the exascale computing applications, and how can we impact the standards? So we're very heavily involved in the standards communities, looking at things like OpenMP and OpenACC for the on-node work and exploring, again, new features and helping with the standards community efforts. Performance portability libraries, I just mentioned that, abstracting away the details of the architecture. LLVM, so looking at different compiler technologies, particularly when it comes to Fortran support, and making sure that we've got a lot of different options that will be available to the applications to get good, hopefully, performance out of their compilers. Performance tools and analysis tools, PAPI, TAO, the HPC Toolkit, again, widely used technologies where we're looking at new features, looking at power management, different kinds of counters for the new architectures. Math libraries is a big need by the applications libraries, the BLAS libraries, linear solvers libraries, I/O to address the communication issues. So HDF5, again, widely used, and we're very involved with that. MPI/I/O, Audios, which is a tool developed at Oak Ridge, and then viz and data analysis. So looking at a lot of VTK-related tools, peer review. What do we need to do things in situ rather than post facto? So the investments in the software technologies that we're making, I've listed several here in terms of the kinds of things that we're investing in so that you can get a sense really of what we're looking at. So when we're talking about things like MPI and OpenMP, so for MPI-CH, one of the things that we wanted to do was really explore how do you incorporate hybrid programming models directly into that. And what about deep memory copies in OpenMP? That's one of the biggest gaps in OpenMP is the ability to represent that in the standard. So we're exploring that. We've gathered requirements from the application teams that are part of ECP. Where would you need this? Where would you use this? Developed some prototype implementations. And now we're taking that to the standards community and talking about, is this something that we can get implemented into OpenMPI version 5? So performance portability tools, Kokos and Raja, and encourage you to listen to the talk later today on Raja, but that's one of the biggest concerns that application developers have is how do you abstract away those details of the architectures. For C++ implementations, Kokos has been developed at Sandia National Labs. It's widely used by many different applications. It has an ecosystem for C++ applications where you can abstract those execution models away. Support for alternative models and understanding the benefits. So for example, PGAS models or things like task-based parallelism when you're thinking about the Legion tools at Los Alamos National Lab, and then libraries for deep memory hierarchy and power management. In terms of development tools, again, looking at LLVM, the compiler and the ecosystem around LLVM, we have a lot of different technologies that are looking at that and focused on that and developing a community around that to support the ECP architectures, including support for F18 and the Flang compiler. And then performance analysis tools. I mentioned PAPI and TAO earlier, looking at the new architectures and the new programming models that are being developed and how can those tools help application developers understand the performance that they're seeing or the bugs that they're finding to make their development times faster. Math libraries were largely focused on linear algebra, iterative linear solvers, nonlinear solvers, optimization, FFTs. So many of the things that are widely used. Looking at the performance on new node architectures, strong scaling is important to many of our applications and looking at those kinds of techniques. Multiphysics, multiscale. I mentioned earlier that many of our applications are focused on that. That's something that Exascale enables is multiphysics, multiscale modeling. How can the math libraries be developed to support that? And then increasing the quality, interoperability, and complementarity of the packages. So rather than having a lot of overlap, having a lot of complementarity and synergy between them. For data and visualization, largely focused on I/O. Again, primarily focused on HDF5 as our primary mechanism there. In situ visualization and analysis, compression, and what are the ramifications of doing compression in situ, and then checkpoint restart. All things that are bottlenecks for application developers and things that we need to advance. And then the software ecosystem. How are we deploying the tools that we need through package management tools such as SPAC, looking at optimization and interoperability of containers for HPC systems as one of our deployment mechanisms, and then regular releases of this extreme scale scientific software stack. I mentioned that we contribute to a lot of standards. Here are some that we're actively contributing to. So obvious ones, of course, would be the MPI Forum, OpenMP, the BLAS. C++, this is one where we've taken a lot of advantage of things like lambdas and this performance portability tools that we're developing, and we're trying to get some of the infrastructure associated with that performance portability that's been developed in Cocos and Raja directly into the C++ standard. So that's one way where we're trying to create longer-term sustainability for our tools. So a lot of the products are available for download, many via GitHub. And so, I just threw up, a laundry list that you can't possibly read. But I think the idea here is just to get an idea that there's a lot of products that are available, and they're available to you and to the broader community. And more information is available on our website. So you can tell that the ecosystem is going to be comprised of a wide variety of these software tools. And so part of our effort is how do we make it more turnkey for application scientists to take advantage of these things. And we're doing that through the development of software development toolkits, SDKs, and the extreme scale scientific software stack. So I'm going to spend just a few minutes on each of those before I wrap up. So for the software development toolkit, these are pretty widely used in many different parts of software development communities. They've been less used in high performance computing. I think the ECP provides a unique opportunity where it's bringing together hundreds of researchers that are all pulling in one direction. And so we have an opportunity to try and come together as communities to establish interoperable, sustainable packages with community policies that are tested and rigorous that we've never had before. So I think that's a unique new area that we're trying to create for high performance computing. So again, a key point here is it's a collection of related software products, packages, where we're developing these community policies. So the idea is that each one of these collections makes some amount of functional sense, and the interaction model is really how are they interacting? What are the conditions for compatibility, for interoperability, and what are the community policies that are required to make sure that that happens? So the idea here is that where it's essential, there will be unity in order to achieve this interoperability, but otherwise, the package developers still have a lot of freedom in how they're developing their software, so diversity otherwise. So we're really talking here about horizontal groupings. So if you're an application developer, I want you to think back on the day where you needed to merge, some set of two very large-scale numerical libraries together, both of which depended on some sub-library. In this particular case, think about merging PETSI with Trilinos, both of which might depend on some version of SuperLU. And think about your frustration when you got all the way up to it and then it tried to link and said, well, you've got all these conflicting versions of SuperLU under the covers, and then you had to track that down and figure out why the linking wasn't happening. Building has often been a complaint for application developers. It's a frustration. It takes away from your science. It just takes too long to put these large-scale packages together in ways that are easier. So this is what this SDK effort is attempting to address. So it would ensure that when you have these horizontal groupings of functionality, so for example, a multi-physics application that needs both PETSI and Trilinos, all of which relies on some version of SuperLU or some other version of MPI or what have you, that X equals Y. So the two versions of SuperLU will in fact match. And that can be a huge gain in terms of time, developer time, when compiling and building. So that's really what we're looking at. And so the one that's been around the longest is the one that's focused on math libraries, so XSDK. And this is sort of a general overview slide of what we have in mind when we talk about community policies, team building, quality improvement, et cetera. So the idea is a community policy strategy allows those policies to be developed. And in this middle blue box here, you can see what some of those policies might be. So for example, support a community GNU AutoComp for CMake option. Look at and using a comprehensive test suite. Use a user-provided MPI communicator. These are the kinds of things that are necessary to make sure that you don't have collisions when you're building multiple libraries together. So for the XSDK, for the math SDK, I think they're on the order of 16 or 17 required policies in order to be a part of the SDK. And then there are a series of recommended policies. So have a public repository, not required, but recommended. Run a test suite using Valgrind. These are the kinds of things that help improve the quality of the software as well as the accessibility. So for the math libraries, the only point for this was in 2017, you had a number of the green bubbles that were part of the XSDK functionality, PETSI, SuperLU, Trilinos, et cetera. And about a year later, all of a sudden you've got, many, many more green bubbles. So this is what you're looking for, the number of green bubbles and the number of packages that are now interoperable with each other and can be used together more seamlessly by the application users. So we have a number of planned SDKs that span all the technology areas that I've been talking about, ranging from math libraries to programming models and runtimes, compilers, data management, ecosystem, viz tools, and here are the tools that are being considered for each of those areas. So because I'm running out of time, I'll just skip right ahead here. So the Exascale software stack, it's a SPAC-based distribution of ST products. And the idea is that they are all built together. And once you can build all of them together, you know that you can build a subtree of them pretty seamlessly. So it will leverage the SDKs that I just talked about. And we've had 2 releases, prototype releases of our Exascale software stack. The first one had 24 packages that were fully supported, and the second one, which was just released in January, had 37 products that were fully tested with each other and found to be compatible. If you want more information, you can go to e4s.io. That's the website for the Exascale software stack. So these are the packages that are currently included in E4S. And then SPAC, I just want to mention it because it's a very nice tool that allows for the management and development of packages on high-performance computing systems. And so the pointer for SPAC is here, and the documentation that you can take advantage of. So if you want more information about the software technology projects, it's available in the assessment report that's been released. And the website is provided here. So the final thing I wanted to talk about is collaborations with industry, particularly in the area of software technologies. So I mentioned many, many different kinds of software technologies that are available through the ECP or being developed as part of the ECP. And what I'd like to do is at this point invite the folks in this room to take a look at the software technology website, take a look at the different kinds of things that we're developing, and let us know if there are areas where you would like to explore collaboration. So it could be in developing or just reading some of our papers. It could be in attending some of our tutorials or WebEx type things, ranging all the way down to, for example, evaluating some of our software and deciding, is this something that I want to adopt? Or maybe it's an idea that you really like, but you don't want this particular infrastructure, and then you would develop a similar thing for your own products. So there's all kinds of different areas in which we'd like to engage the industrial community. And I invite you again to take a look at the different opportunities that are provided as part of the ECP, and let us know and reach out to us if there are things that you would like to do. So just to summarize, I think the ECP is on track. It's been going since 2016. It's a large effort consisting of about 100 different research teams, about 1,000 different researchers, working on 25 different applications, about 100 different, 80 to 90 different software technology projects, and working towards integrating all of this for exascale computing. And if you'd like more information, I invite you to visit our website or to reach out to any of the leadership team, including myself, Doug Kothe, who's the project director, Andrew and Eric are for application development, Mike and Jonathan for software technologies, and then Terry and Susan for hardware and integration. And with that, I believe I've left all 17 seconds for questions. So.
Well, the good news is that I finished early, so I'm going to defer those few minutes to you, Lars. So if you have a couple of questions, raise your hand. While they're thinking about it, there's one in the middle there, but I'm going to ask one while they get the microphone there, Lori. So you mentioned something about the event-based processing of particles. Have people, that would result in a speed up? Have they looked at how that could translate to other types of problems, that approach to doing computing?
No, that's a good question. So that particular team is the application team focused on small modular reactors,
okay.
And they're very focused on delivering their science, and that's one component of what they needed to do for their global problem. So I'm not sure that they've actually looked at the broader implications of how that model can be translated to other kinds of applications in other areas. Okay. So unfortunately, probably not.
Okay, well, there's an opportunity.
Hi, Addison Snell with Intersect 360 Research. Thank you for an outstanding presentation. You talked about co-design with respect to hardware providers, and of course there's the implicit assumption that we'll have commercially available hardware products. With respect to software, does it make sense in any of these cases to extend the co-design principle to any of the commercial software providers in any of the industries to work with them on developing commercially available scalable software products?
I think it could. It'd be interesting to know what you might have in mind in particular. I'm not familiar with your company, and so if there's something that you have in mind in particular, I think that would be good to know. So I know a lot of the vendors, for example, commercial vendors, are providing things like the MPI implementations, OpenMP implementations, and so a co-design process where the requirements that are derived from our numerical libraries, from our applications that feed into the standards could then also be used in a co-design process with the vendors who are providing that commercial functionality. I'm not sure if that's quite what you had in mind, but that's an example off the top of my head that I can think of where that would make a lot of sense. But I'm happy to talk to you offline about something more particular.
If you have one more question. Oh, there's one in the back there. Okay. We'll run the mic up there.
Thank you. This is Lou from Halliburton. Excellent presentation. Thank you so much.
Thank you.
So one question regarding to you mentioned about the horizontal versus vertical. Especially you support the SDK. Have you facing the issue like the more application, the more requests from different groups, actually you have to resolve the conflict on the requirements priority-wise? Who gonna resolve first? If the requirement actually have conflicts, how you achieve the common target versus vertical? Have you think of? I understand you may have different versions to running from different application. Have you considered using containerization mechanics to kind of help on that?
So we, for the second question, no, we haven't considered that technology. We've been relying a lot on SPAC, the package manager that I mentioned. I didn't have a lot of time to delve into it in detail, but it basically provides the mechanisms that we need to understand which versions are being compiled with and ensure that consistency checking. And so one of our early targets for all of our SDKs is that they be SPAC enabled, SPAC package enabled, so that they're part of that infrastructure, and so that checking for those sorts of conflicts can happen through that mechanism. So that's the mechanism that we're using for that kind of a conflict. And now I'm trying to remember the first part of your question. Right. How you balance between, especially when you have conflicts on. Yeah, so one of the things that's really interesting is that there have been many efforts over the years to develop community policies where these sorts of conflicts across the horizontal layers arise all the time. So I was involved in one that was looking at unstructured grids. There have been ones that have looked at linear solvers in particular. This one is more focused on the requirements that you need just to avoid, for example, collisions in namespace. So it's not trying to get at interoperability at kind of that deeper software level. And even there, it took several years for that community, the math community, to come together and have enough of a common understanding of how they did their work as individual packages and then as a community to derive what those policies should be. So that effort has actually preceded the ECP, and it's been going on for about 4 years, and now is rolled into the ECP. But yeah, it took a long time for that community to come together. It's a challenging task.
Please join me in thanking our speaker. And I just want to add that the two names you did not put up there, which actually is people that many of you know. This is Dave Martin and Susie Tickner. They are working actually quite closely with us. So thinking about how we could maybe work with them to do some sort of training or hands-on and using
Well, I know there's
conversation.
there's a follow-up
call on that. So stay tuned for that.
Yeah, so talk to Jan and he can get you in touch with us too.
Yeah.